and has a position at the Delft University of Technology as well. He is very active in the field of catalysis simulation and flows through active porous media. We have been collaborating in the recent years, and we have also delivered a book chapter together. So it's a great pleasure for me to introduce him to you. And please, Harry, the floor is yours. You have 30 minutes for your talk, and then 10 minutes for the questions. Please.
Okay. Okay, thanks for the introduction. And also thanks to the organizers for inviting me to give this plenary. You see my opening sheet. It's very green because green is the color of Ireland. The university has just switched to this national color. I don't know whether you are familiar with St. Patrick's Day in March. There are even parades in the US on St. Patrick's Day, and then everyone is clothes are in green and green illumination everywhere, and so that is why it's very, very green. Then on the next sheet you see my title. You see that I'm in Limerick and also in Delft. The font size of Limerick is bigger because that's my main affiliation. You may wonder where Limerick is. Well, that's on the map here. It is this is the island of Ireland. Dublin, the capital here, but Limerick is on the west, and they call it in Ireland the Midwest. You know where it is. And why did I get there? Because in 2012 or so, 2011, the University of Limerick started the Banal project. You see here the description, a 52 million research and teaching project. And in the context of that, I joined University of Limerick in 2013. And well, the University of Limerick is doing pretty well. You see here that the Sunday Times Good University Guide elected the University of Limerick in 2019 and in 2015, I think, as a university of the Irish University of the Year. Okay, you see the Banal building here on the right. That is a brand new building built in the context of this Banal project. So on the next sheet, where do I go for the next sheet? Why doesn't it work? Something.
You can hide this little bar down. You can hide it.
Oh, hide it, yeah. That's it. Yeah. Okay. So you see again here on the left, upper left, the new building. Banal was a crystallographer, so that explains the outside appearance of this lecture room. The new library extension at the University of Limerick, the White House, that's really called the White House, where the university started. You see the campus here on the right upper corner. It's a very green campus with on both sides of the river Shannon, and that's the largest and longest river in Ireland. You see the number of students, you see the number of faculty at the Banal Institute, the number of PhD students, postdocs, and that's a bridge over the river Shannon. So to make you a little bit more familiar with University of Limerick. Then to my research group. In Limerick, I'm supported by Dr. Oris Shart. He is a lecturer since a couple of years in Limerick. Two research fellows were here for a couple of years. And on the Delft side, you see it's a longer list. It started earlier, and there are more PhD students and students involved, so that makes the list longer, but the contribution, of course, in proportion to the time they're spending here. Several of the Delft people spent periods in Limerick, so there's a close interaction between my two research groups. And it's not my research group in particular in Limerick. I'm working on different topics as well. And all these guys contributed to the content of my presentation, so I really acknowledge them for their contributions. Then about my presentation. This is just to make clear where I come from. I'm a chemical engineer by education, and that is where I start my research from. So it's always start with chemical engineering applications, with chemical engineering problems. In many cases, as a result of companies who came to me and said, we would like to have a better understanding of the manufacturing process. Can you help us out? Well, then I do that. And then in many cases, I turn to lattice-Boltzmann techniques. For chemical engineers, lattice-Boltzmann is a tool, not the focus of their interest. So it's a tool. And I think there are many reasons why LB is preferred over finer volume techniques, because in many cases it is faster. And because you are faster, you can go to a higher spatial and temporal resolution, so they give you more information on what's happening on the mesoscale. So that's making a difference, a better understanding, that making a difference for a better understanding of the manufacturing process in industry. So I always start with an industrial question or industrial problem, or industrial issue. Well, it's not only a tool in comparison with finer volume techniques, but in many cases, I think it's also a substitute for experimental investigations, not because experimental investigations are more expensive, at least if you use sophisticated techniques for looking at what's going on smaller scales. So I think that with LB, you can go to a higher spatial and temporal resolution and learn more than you can in many cases do. Some cases can do with experimental investigation. So this is a little bit about the background and why I have turned to lattice-Boltzmann techniques. I started lattice-Boltzmann in 1996 on single-phase flow stirred vessels, cyclones. So that was most single phase. But you see from my title that we will now talk about emulsions, so that multiphase, and chemical reaction, that's again single phase. That's two focal points of my current research program. Well, for multiphase flow, I prefer the multi-component pseudopotential lattice-Boltzmann model due to Shen and Chen in 1993 or so. I think that they started that. And there are three important elements in that. That's the intracomponent forces, and that is due to pseudopotential that is related to equation of state. And there is an interaction between components, and the important parameter is the interaction strength G. And then, of course, there is a relaxation time, and that is not very different from the usual, the common LB single phase, except that you could use multiple relaxation times for the components, but so far I'm restricted myself with a single relaxation time. And then a very important reason why I prefer the pseudopotential lattice-Boltzmann is because the aspect of the spontaneous phase separation. That's really the reason for me for embarking on a pseudopotential LBM, because it is spontaneous, so that is just a result of forces you impose or model on the mesoscale. So that is the main reason you do not need separate equations to find out where interfaces are. So the intracomponent aspect that is here is pseudopotential related to equation of state. You see here two examples. The original relation for the pseudopotential that introduced by or used by Shen and Chen in 1993. So they use this equation rather than just the potential being equal to the density only. So this is more suitable because of stability reasons for the LB schemes. And here is an example, the Redlich-Kwong, when you use this equation of state, and this is how you introduce this pressure into an expression for the pseudopotential. And this equation of state and the temperature, the relative temperature, so the temperature divided by the critical temperature, these two parameters dominate the distribution of a component over the two phases, paper phase. So that is in a nutshell what the pseudopotential is. Next sheet, we turn to the intercomponent forces. So that is the interaction between two or more components, and that is taken care of by the interaction strength G. Two subscript for G possible. So if they are similar, for instance, 1, 1, and if that is the G parameter is negative, then the parcels of that component attract each other, and then they form a liquid. An ideal gas is if the G value is 0 for that component, and a G parameter that governs the relation between the interaction between component 1 and component 2. And if that is bigger than 1, then you get repulsion, and the result of that these components are immiscible. You get automatic phase separation, and surface tension, facial tension will develop as a result of these automatic phase separation. So you don't impose a surface tension; it's a result of the simulation. So that is in this. That is explained in this scheme. You see 1 and 2; they repel each other, and the green ones attract each other, and that is by a negative G value. And then, of course, there is a relaxation time, but that will not. That is pretty classical with the LB model. Just an example of spontaneous phase separation. Starting from a random distribution, we look at the spinodal decomposition for two components with the parameters here underneath, and then you see how, as a result of the superpotential method, the two phases separate. And red is always a high value, blue is a low value. So this is a component that collects into the spheres, and of course there is diffusion of these components, mutual diffusion, and so then as a result you get gradual growth of the droplets. That keeps going on for quite a while. From also crystallization theory, that the bigger particles always grow. So that is one of the main reason. And then, of course, if there is coalescence, then you get additional motion in the outer fluid, and that also helps, contributes to these to the growth of the droplets, the coalescence. Okay, so that is why I really like this. Then, of course, you should. Is this attractive? Yeah. Well, we use this, for instance, for a Taylor bubble in a microchannel. Was one of my first papers on LBM multiphase flow. You see here the Taylor bubble in a microchannel, depending on the capillary numbers, viscosity over surface tension, and the Reynolds number. These Taylor bubble has different shapes, either rather symmetrical or 5 is more torpedo-like, and it all depends on the capillary numbers and Reynolds numbers. And we did this for a ratio, density ratio of 8.7, so 2 liquids, if you like. And is this qualitatively is this correct? Yeah, it looks familiar. Quantitatively, you see here the film thickness between the film between the Taylor bubble and the wall, that thickness is called delta, is made non-dimensionless with the channel height, the channel diameter, and as a function of the capillary number, you see here lots of data, and in red our data. So we started with a relatively best grid 64 times 512. Then you see that the higher capillary number is fine, but you get deviations here. But if you if you increase your grid resolution, finer grid, then you see the triangles, then they really follow the line. Should be also for lower capillary numbers. Yeah? And you see all the conditions that we used, and we also used the G parameter for the interaction with the walls, the W's for the wall. Yeah, and able the lighter component and be the liquid, and so minus sign, and a 0.2 for the interaction between the two components. Okay, so this was just my first exploration. We looked into many more details how to do that, and in particular, we looked at the thickness of the interface between the droplet here, the droplet in this 2D square. The radius is 30, so the size is 90 or 100, something like that. So it's a droplet in a gas, and we show here how the interface, how the phase separation and the thickness of the interface depends on the relative temperature, so temperature divided by critical temperature. And you see if the relative temperature is always 0.95, you get separation is not that good, and you have a big interface. But if you go to lower relative temperatures, then you see that separation is much more explicit, and also the slope is steeper, so the interface is thinner. And we did that for a particular technique. So it's the equation of the Carnahan-Starling equation of state. Yeah, and we use this technique for the many variants, and you can find more details in a 2015 paper. Is it correct in terms of the phase separation? You see here for two non-ideal components with Carnahan-Starling again, how our simulation results in points here that are very close to the liquid line, and also very close to the vapor line. For the purple is with no interaction between the two, so only a single component. And if there is an interaction with the second component, then the vapor constant, the vapor density decreases slightly. Yeah, so that is to see the effect of TR on the density of the two phases for a single and for two components. Another issue is the spurious velocities. Well, people in the Lattice Boltzmann world are worrying about the spurious velocities. So you see here this for a simulation in comparison between three techniques: open foam, fluent commercial solver, and pseudo-potential Lattice Boltzmann method. All the details are in that paper here, in these two papers. You see that we start with the square droplet and then subject it to all the equations and see how the spherical droplet develops for a droplet in a gas, so density ratio 1000. Then you see that this is the spurious velocities for the pseudo-potential methods, and you're familiar configuration of these spurious velocities. But you see that on the square grid, also the final volume methods suffer from that, and in these cases, spurious velocities are much bigger than in the pseudo-potential Lattice Boltzmann method. Well, and you can cure everything, but well, I thought that it was a fair comparison, that we should not, at least my group and myself and all my companies I'm in contact with, do not worry too much about these details. I keep in mind that in many chemical processes, you even know the properties of your fluids not that good, and the conditions, and so this falls within the usual bandwidth of errors. Well, you see where we did it on, and the time that you took going from a square droplet to the spherical droplet was with open foam 250 seconds, fluent something similar, and the pseudo-potential only 22.5, and same single processor. And so we really can see the attractiveness of the PowerPoint of the pseudo-potential method in terms of computational time. And then we go to finer grids and use part of the time advantage for getting a higher spatial resolution and that type of thing. So, okay, so now with shear, so we're gradually getting to a process. So this is, again, a spinodal decomposition technique for two components with shear. This is the movie, so the upper wall moves to the right, the lower wall moves to the left. And you see how the shear affects the coalescence behavior. Probably promotes coalescence under these conditions. Not breakup. See that coalescence is happening. And now you see this is for the component that's high in the outer phase and low in the inner phase, in the droplet phase. and you see the thickness of the interface, and that is, well, you can get it better, but essentially qualitatively this is correct behavior, I think. Okay, so then breakup of a droplet due to shear, so under different conditions. You see, you already saw that happening here in the lower one. Yeah, so this again is for a Reynolds number of 7 and a capillary number of 0.21. Then you get breakup of this initial droplet. You see here the parameters. You also see that it is the equal density of the two components. So that is, but if your capillary number is slightly lower, then you see that there will be no breakup. There will be deformation, but no breakup due to the lower capillary number, higher extension, if you like. It takes that form, but it keeps that form, and with a little bit higher capillary number, then you get breakup. So, well, is this 0.21, is that a reasonable number quantitatively? Well, then we compare with two other computational techniques, free energy technique and the VOF method, and you see that we are close, not exactly the same. Who knows what is the real value? And of course, yeah, I have to admit it was a 2D simulation. The other two are 3D. So there are small differences. There can be small differences, but at least it gives you a good impression of the process of interest. Then in the next sheet, we compare that for different circumstances with simulation results by meter of free energy. Lattice Boltzmann methods earlier, some 10 years ago, 12 years ago, and you see that our method is gives a rather similar result, not exactly the same, but pretty much same for different values of the capillary number. So this gives confidence that our method and our code are working correctly. So now we are going to introduce a surfactant, so 3 components. Yeah? And so that means there are 3 G values between the 2 main components, between the alpha component and the surfactant, indicated by an S, and the second component, the surfactant. And so 3 components. You see 3 relative temperatures. We took them here differently. You see the side of the computational domain. This is one of the 2 main components. Again, the spinodal decomposition process. You see that this is the droplet phase that you see here. The droplets are high. In the droplet, the concentration of the density is high. Here you see the surfactant. And what you see that as a result of the choice of our parameters, the surfactant collects at the interface. You see yellow and red, and so are only in the interface, with the surfactant hardly present in the outside and a little bit higher concentration inside the droplets. So by tuning these parameters, you can really mimic the behavior of a surfactant. Here, if we look at have a closer look on the results, so we have again here our periodic box, droplet in the middle. We look at the concentrations and the densities on this line through the middle. Then you see here for the alpha component, the beta component, the 2 main components, and the surfactant. You see that the alpha component is the droplet phase, that the beta component is the outer liquid, a very rather thin interface. And of course, a few lattice distances. And here you see how the surfactant collects in the interface. At the interface, a very low value outside and a little bit higher value in the middle. And you see here how the density, the concentration profiles behave, and what this interface thickness is. And this is a non-dimensional density, so that every thing is between 0 and 1. And here you see for the surfactant how the distribution of the surfactant over this line distributes as a result of this G value, with the G between alpha and surfactant. Yes, if we keep that 0, then there is no collection then the surface surfactant does not collect at the interface, it's everywhere. Yeah, but if we increase the G value between alpha and the surfactant, so this is the highest value, then you get a real high peak value. And then the difference between the outer concentration and the inner concentration is because we take this assumption for the interaction between the beta component and the surfactant. So that explains the difference between inner and outer concentrations of the surfactant. Okay, so now a breakup of a droplet with a surfactant. Therefore, that is of course what we are interested in. What does a surfactant mean for the breakup of droplets? Well, this is a movie again, and I will show you how it develops. And you see here in the plot, the column is for the surfactant concentration. So you really see that the surfactant collects at the tips. Yeah? So the droplet is elongated, upper wall moving to the right, lower wall moving to the left. And you see how the surfactant collects at the interfaces. You get Marangoni effect, and then we'll show this again. Maybe that's nice. So here you set immediately the deformation and a very gradual process of thinning of the center here. And then when you think that there's nothing happening anymore, then there it goes. Yeah. So and then you see the two droplets, but still the typical shapes, and still the surfactant at the tips. And if you look at the snapshot here, then you really see how fine the grid is. You see all the velocity factors, local velocity factors. You see how they go around, and you get a circulation here these periodic walls, and you see in the color code where the surfactant collects. Yeah, so this is the density of the surfactant density. You see all the conditions that we used, and well, of course, you can vary about that. The capillary number of 255. Yeah, so it's a little bit different from what I showed you earlier. So that is the effect of the shear, of the effect of the surfactant. Here we show that the effect for the same capillary number, 0.271, almost equal Reynolds numbers. And then you see that without a surfactant, the droplet breaks up, say, well, the dimension is time 37, and with the surfactant that is postponed to 43. So the surfactant delays the break-up process. That is, at least for these conditions, that's the case. We had a better look at that, and then we see here the break-up time, non-dimensional break-up time, as a function of the capillary number, no surfactant and with surfactant. So you see here the two lines cross. If your capillary number is lower than 0.26 or something like that, depending on all the parameters, then you see that surfactant delays the breakup, and with the higher values, it's the other way around. Yeah, so that is an interesting, this is a very preliminary result, but I really like to show you this. Then emulsification can not only do due to shear on a large scale, or but also in the turbulence flow field. So we do here emulsification due to turbulence in the 3D periodic box, and the number of the simulation details are given here. So the density and the viscosity ratio is 1 for the time being, and all the and the initial condition is a single droplet of a specified full volume fraction, and then we will turn on the turbulence. So we use forcing turbulence. All the details are in the paper in the Journal of Fluid Mechanics. I just like to show you here the results. We did a.
Sorry, Harry, you have 5 minutes, please.
Yeah.
Okay.
Okay. Yeah.
Okay. Thanks.
So that all the details here. This is an example for the breakup of single droplet, and you see on the right-hand side the number of droplets in the process, and you see how that increases dramatically and then stabilizes more or less in a very fluctuating process. So that is what you can see if you subject the droplets to forced turbulence in the periodic box. With higher volume fractions, you get something similar. So you see, but of course it becomes even more complicated. Well, there's too much details to really be understood here. So that is why we look here at such a single droplet, and the color code. So you see how the droplet is breaking up, and the color code is the entropy, so the energy dissipation. So you really see here how dynamic the whole process is. Well, this is qualitatively. We looked at, we'll skip this one. We look at the turbulence dynamics, at the particular Reynolds number, 10% volume fraction, and there are four variables here, and that is the kinetic energy of the turbulence, the number of droplets, the entropy in the liquid, and the energy, the interfacial energy. Yeah, and you see there looks to be some periodicity. Well, this is between non-dimensional time between 0 and 2000. If we zoom in a little bit, between 200 and 1000, then you see here the kinetic energy, and there are some maxima. There's some repeating maximum or minimum and so on. Here is the entropy. And you see the periodicity here even more clearly. You see there is a time delay that the entropy follows the kinetic energy, but with a delay. And then the number of droplets is even further delayed, with another time lag. But we also see that if you look at the kinetic, in the facial energy, that the maximum in the facial energy peaks before the number of droplets. So that is, you can learn all this from these simulations, that you can't do that with experiments. So we need simulations, very detailed simulations. So then we think there's a cyclic dynamics between one extreme with a low interfacial energy and a high kinetic energy of turbulence. And here on the other side, just the other way around, it's a large interfacial area and interfacial tension, interfacial energy, and a low kinetic energy. So you see here a small number of droplets, and here a very large number of droplets. So the frequent breakup in this way, and then here we get coalescence again, and that we think that that's the circle. You see here that for the number of droplets indicated for things. So drop formation at an interface. Yeah, that's a movie. It's 2 components, pseudo potential with psi, the potential just equal to the density, and we can see how we can do drop formation here with gravity working only on the drop liquid, not on the outer liquid. So that is that's nice. This with 2 components. These are the snapshots, so you see how the droplet starts falling with the neck elongating and so. And this is with the surfactant. So the lower is with the surfactant, and that is really so 3 components. So that means really that the drop formation is affected. And you also can see that the surfactant collects at the rear of the droplets, and so is driven away from the front side. There's low concentration of surfactant here, and you see higher concentrations at the rear sides. So, but that is for equal density between the 2 components. If we really like to introduce density ratio, then we have the idea that we adjust the sound of speed by introducing this definition of the beta potential function in the second phase. So by doing it this way, and that means that the total pressure is given by this expression. So with the parameter here that is different from the regular speed of sound for the other component. So that is the way how we make a distinction between the 2 density phases. But this is a work in progress, and we didn't manage to get results in time for today. So that was something about the equation of the velocity of sound. Turning to the chemical reactions, I need a few slides. So in chemical reactions, the chemical species have different molecular mass. And also the product have again different molecular mass. That is that's well inherent to chemical reactions. We're talking about single phase. So and the velocity of sound is given by this expression when you see here the molecular mass. So can we mimic the role of the different molecular masses by tuning the velocity of sound? Well, we then found out that we should combine that with also using an extended lattice and an extended velocity set, and also use a modified liquid distribution. All the details are in this paper, just for single phase flow without reactions. And then we introduce the tuning parameter gamma, which is the ratio of the 2 velocities of sound squared. And this is, I think, not only important for chemical reactions, but also if we talk about surfactants and with a very molecular mass. So the test case in that paper in 2018 was a Taylor-Green vortex. This was the initial condition for density and velocities. And over time, it will decay exponentially due to viscosity. It's a simple model. If we use different tuning parameters, gamma 0.8, 1, and 1.2, and we do that on the D2Q9, then you see that you get a spread in the results. But if you turn to D2Q13, then everything nicely falls together on the analytical expression. Well, then we use this for chemical reactions. A simple case, 1D. This is a wall where we prescribe particular concentration for the component. The chemical reaction is here the other wall due to catalyst. And this is the X direction. There's a dump column number, the reaction rate of diffusion. And we see that if A gives 1B, so the molecular mass doesn't change. For different dump column numbers, our code predicts exactly the analytical curves. So that is this green one is this line here. So that's for gamma is 1. If we turn to gamma is 2, so for the case that A gives 2B for dump column number of 1, and we both, then you get different curves, different concentrations and densities, and both cases have been done on the D2Q13 lattice. This is on mass average basis. This is on the mass average basis with the total density constant. We can also do this on a molar average velocity with the total concentration constant, and this is something similar. And we see here that our code predicts it for A goes to 4B. And then also our data point pretty well match the analytical technique. And the last case is a tubular reactor with laminar flow. The other one was no flow. Now we have laminar flow in the tubular reactor with the reaction normally occurring in the pipe where we start with a particular concentration, Ca. A reacts on the wall to 3B, so that gives a gamma of 1.5. And you see here the prediction of pressure, velocity, concentration of A and concentration of B. Everything on the D2Q13. The pressure is not exactly constant, but it is only a variation of 1%. So we're trying to get a better. Not sure exactly how we managed to do that, but that will not seriously affect the development of the velocity and the two concentrations. So that brings me to the concluding remarks. Attractive feature of PP is the automatic phase separation. Enables simulate the behavior of a surfactant in droplet breakup. Periodic boxes are suitable, both in shear and in turbulence. Emulsification, cyclic behavior under turbulent conditions. Tuning the velocity of sound is useful, but not only the velocity of sound, you have to do more. The lattice has to be extended, and the equilibrium distribution should be adapted. It gives them inner view on the process of a microscopic level, and that is why the companies I'm working with are very highly interested in. It requires a high degree of LB expertise. So there are many high sensitivity of the LB method to a lot of parameters, in particular in multiphase flow. But I think that is a very versatile profile for a wide variety of cases of interest to industry. And well, that's my presentation. And thank you for your attention. Use a little bit more time than Apple. Yeah.
No problem. Thanks, Harry, for this interesting talk. We have time for one quick question from the audience, if there is one, please.
May I ask a question?
Yeah.
Please, Alex, of course.
So you gave some interesting presentations on surfactant simulations. Now, when you have surfactants, often you also have a disjoining pressure which would inhibit the merging of two droplets, right? So you look at the phase separation where you would be able to form like a micro-emulsion phase. Is that something that would come out of your current implementation of the surfactants?
I think that we most of the time no, that we did not pay attention to that aspect. I think most of the time we spent time on the breakup, but I think that also in the there must be coalescence 2. I don't know whether I can show that here. It's visible. The emphasis has so far more been on the splitting and not on the. It's difficult to say here because it is 3D, so it's also move out of plane. It's difficult to say, but it's an aspect that we need to consider. But that's an example of the sensitivity of the LB parameter, the LB model for all these effects, and how do you take them into account? Yeah, so that is illustrative of the difficulty of running LB simulations for multiphase flow. Yeah, thanks for the suggestion.
Thank you.
Okay, thanks, Alex. We have just another question. If it is quick, please, Dr. Hosseini, Sayed Ali Hosseini.
Hello. Thank you very much. Can you hear me?
Yes, sure.
Yes, we hear you.
Thank you very much for your interesting talk. I just had one quick question about the introduction of variable sound speed as a function of the different components. I wanted to know, was there any difficulties with just using the standard non-isothermal expansion of the equilibrium distribution function? Because you can achieve the same dependence of the sound speed on the mixture properties by just using a non-isothermal equilibrium distribution function.
This always is isothermal, huh?
Well, you can keep the isothermal nature because the non-dimensional temperature, theta in this case, would be the ratio of the mixture average R multiplied by T divided by your reference sound speed, which is CS.
Yeah. I'm not quite sure how to respond to this question or suggestion, because we just focus on isothermal behavior. Huh? There was also with the paper, and there was a question from the reviewers. This is just to deal with the differences in molecular mass.
Thank you very much.
Yeah.
Thanks. Thank you very much, you all. Thank you, Harry, for this nice talk. So let's thank our speaker one more time, please. And I leave the floor to my friend Giorgio Amati as a chairman, and we will start with the technical session. Okay. Thank you, Giorgio.
Okay.